In this video, we continue our study of microcontrollers, this time focusing on digital and analog inputs to the microcontroller. Let's consider first the traffic light circuit. We've looked at this already, and we know that this is the circuitry that we would use to build a traffic light, where we have the three diodes, red, yellow, and green, that we put each in series with a 220 ohm resistor attached to a digital pin. And then all of the diodes are attached to ground. So we would like to work with this circuit now and make some modifications to it. But let's consider first how we interact with it. The pins that we use, the digital pins, we set up as output pins because we were directing certain voltages to be associated with these pins. Within the setup function, we look at a pin, and digital pin 6, say, we could set as an output pin. And then within the loop function, we can use the digital write function to write high or low to pin 6 if we specify the pin. This is the way we interact in the sketch that we write to make the traffic light work. And these are the output pins, and we use pin mode and digital write to control the voltages that are associated with these pins. But now we want to add a pedestrian button. So if you have ever used a crosswalk, which you probably have, you know that you come up to a crosswalk and sometimes there'll be a traffic light associated with it. And if you would like to cross the street safely, then you press the pedestrian button and wait a little while. And then the traffic light will turn red and stay red for a while, and a walk light will come on that will tell you it's safe for you to cross the street. Now, to activate this traffic light change, we are interrupting the usual cycle of the red, yellow, green. Then what you're doing here is you're pressing the button and initiating the interruption. Okay, you initiate it, the interruption occurs, you can cross the street, and then you're done. The way we're going to do it is a little bit different. The idea here is, yes, we want to press the button to interrupt the traffic light cycle, but in this particular case, we have to keep pressing on the button to keep the cycle interrupted. When the button is depressed, we want to make it so that only the red LED is illuminated. And we're going to use this button shown on the right. This push button, it's got a button on the top, two legs that are both the same length. So it's a bidirectional circuit element. It can be inserted into the board in either direction. We just want to make sure that the two legs are not inserted into the same row, because then they would be connected to each other and you wouldn't be connecting them to other things. So let's consider the nano again. The digital pins are the ones that we're interested in using. And these are pins D2 to D12, and then D13. And the idea here, if we let D6 be an output pin, is, as I said before, we set the pin mode to be output, and we write high. And that corresponds to placing 5 volts at that pin, ensuring that 5 volts is the voltage at that pin. If we instead write low, use the function to write low, that means we are placing 0 volts at that pin. And to get the blinking lights, this is what we do, is we alternate between high and low at the pin. And that's fine because it's a digital pin. Digital pins are set up so that you have one of two values, off or on, high or low, okay, that kind of thing. Now, we can also set these pins to be input pins. So instead of specifying the voltage at the pin, in this case either high or low, we instead measure what the voltage is at the pin. So first we have to use pin mode to set it to be an input pin. Let's say it's pin D10 that we want to do this with. And we can use the function digital read, specifying the pin to determine what the voltage is there. It can be anywhere between 0 and 5 volts. If we detect high, something greater than 3 volts, it's called high. okay, if it's anywhere 3 volts or higher. If we detect less than 1.5 volts, then that's called low. But if we read some value that's in between, then it's not clear what will be returned. It could be high or low. Those are the only possible values. And it's random. So we really don't want digital read to detect a voltage in that range because we're not going to get a reliable answer if we do. We want to be certain that if we get high back, what that means is the voltage really is greater than 3 volts. If we get less, and if we get low back, it means the voltage really is less than 1.5 volts. So we have to make sure that we set up the circuit so that we're going to see either high or low. Either high or low with no ambiguity. Here's the way we can set up the circuit. First of all, we take the basic circuit that we used before to set up the traffic light, and we are going to augment it a bit. We already have attached to 3 digital pins that we're using as output pins, and we've also attached to ground. And we want to attach to 2 additional pins. One, a digital input pin, so one of the other digital pins we're just going to identify as an input pin. And then we're going to also identify the pin that is labeled 5V, meaning 5 volts. Those are pins, 2 additional pins that we need to set up this circuit. The button is placed in the circuit. It's shown here as something that's got a vertical line with a little handle sticking out perpendicular to it, and that's the notation in the circuit for the button. And we see we also attach to a 10 kilo ohm resistor. Okay, when the button is up, which is the setting that we see right now, it means that the 5 volt pin is not connected to the rest of the circuit, and that means that no current can flow through here. So I, as it's labeled, has to be 0. Now, at any given time, we're going to have current flowing through one of these diodes. Well, during the time when the button is up, meaning we want the traffic light to cycle as normal. We want it to cycle through green, yellow, red, green, yellow, red. So that means that one of the paths that includes a diode is going to have current flowing in it, only one at a time. Which one it is going to determine which light is on, right? It's going to be which part of the cycle we're in. So what happens is at the bottom here at the wire, we're going to have current flowing. I'm calling it ID, meaning that it's flown through a diode. It flew through a diode. Flowed through a diode, yes, flowed through a diode. And then it's going to make its way to this junction. And then here we have 2 possible paths for the current to follow. One is just a wire with no resistance, and it attaches directly to ground. The other would flow through the 10 kilo ohm resistor. So what current tends to do is it wants to go in the path that has less resistance. And so here it's very clear that the path that the current is going to take is going to be just directly to ground. Now, if there was some resistance along this path, then depending on how much there was, some portion of the current would flow along the path and the other portion would flow through the 10 kilo ohm resistor. But since there is no resistance, that's the way that the current is going to flow. There's going to be no current flowing at all through the 10 kilo ohm resistor. And that means that the voltage, since there's no current along there, that means that the voltage at the digital input pin will be identical to the voltage at the junction where ID meets the 2 wires where it's trying to make a path decision. And that's going to be identical to what we see at ground, which is 0 volts. From 0 volts, if we go down through the arrows, down the wire, there's no voltage change, no voltage change. So down at the bottom, the voltage is 0. And that means also, since there's no current flow through the 10 kilo ohm resistor or through this wire that connects to the digital input pin, that's also at 0 volts. So we would expect that the voltage at the digital input pin in this scenario will be 0 or low. So when the button is up, the voltage at the digital input pin is 0. Now, if we look at the other possibility, when the button is down, then there is a complete path, a way for current to flow from the 5 volt pin. and it will flow. It goes through, and the current is going to all go through the 10 kilo ohm resistor. The digital input pin is effectively at the same voltage as the 5-volt pin. All the current will flow through the 10 kilo ohm resistor, and the current will be very small. This 10 kilo ohm resistor is known as a pull-down resistor. This ensures that the digital input pin will have its proper voltage. When it's supposed to be 0 volts, it ensures that. It acts as a drain for current. So the assignment that's associated with this circuit is to build this circuit and to also develop the sketch that will be used to control the circuit. So this means we have to build the circuit that's shown and write a sketch to accompany it. What we wanted to do, first of all, is to cycle through the red, yellow, and green light sequence as it has done before. And that would be what it would do when the button was up. But when the button is depressed, we want it to be that only the red light should turn on and stay on. The cycling will stop while the button is down. I would like you to upload the sketch to Canvas and to also measure both the button up and the button down voltages at the digital input pin. Now nominally they should be 0 and 5 volts respectively, but they might not be. So please submit these via Canvas. When you submit the sketch, put the voltages in the comment box with the submission. Bring your working circuit to the next class and submit all of the Canvas materials before the next class. Okay, now let's go back and look at the Nano again. So what we have here is the digital input, the digital pins, which could be input or output pins, but there are other pins on the Arduino. There are also analog pins, and they are labeled A1 to A7. We know that with digital things, you have 2 possible values, on or off, and for these pins, on corresponds to high or 5 volts, and off corresponds to low or 0 volts. There are only 2 values, right? But with analog, you can have a continuum of values. Really, any voltage between 0 and 5 volts is possible. So when we're writing to a digital pin, we first set the pin mode to output or input. And when we specify the pin, we just use the number. We don't have the D in front. And we use digital write and digital read to work with it. Now, when we're using an analog pin, we can set the pin mode to input, and we do have to specify that it's A6 or A2 or whatever the pin is. Now, to deal with what we're reading, we want to set up a variable to capture the value that is returned by analogRead. So when I execute the function analogRead with the analog pin as the argument, what is returned is the value of the voltage at that pin. So I am capturing it by setting x equal to that value. Now you'll notice that I have declared x as an integer, and I've set it equal to 0 initially, and then I'm setting it equal to whatever is returned at A6. And that's great. The only thing is that we're expecting values between 0 and 5 volts, and they could be things like 0.9 volts or 2.5 volts or something like that. So those values are not integers, and yet we're capturing what analogRead returns with an integer variable. So then we have to ask the question, what value does the analogRead function return? Like, why is it that if it's something that could have a decimal point in it, we are using an integer to capture it? We know that the voltage range that can be detected there is between 0 and 5 volts. If analogRead detects 0 volts, 0 is going to be returned, which makes sense. But if analogRead detects 5 volts, it doesn't return 5. It returns 1023, which is not expected. So then The question is, well, why? Okay, now you'll notice that 1023 is an integer. So then it makes sense. Okay, then x that I set up to be an integer can handle that. So I'm going to get some value between 0 and 1023. So if I get some value in between, it's going to be some integer number that falls between 0 and 5 volts. It's going to fall between, what's returned falls between 0 and 1023. So why 1023? What is the significance of 1023? So to answer that question, we need to look at number systems. Because the way that we look at numbers when we're reading them and we work with them as human beings is different from how computers work with them. We use base 10 numbers. We have 10 possible digits that we can use to describe numbers, manipulate numbers, and those are the digits 0 through 9. But computers use base 2 numbers. And when you have base 2, what you mean is you have only 2 possible digits that you can use. And we've chosen to label them 0 and 1. That's it. We have to describe every number using just 0 and 1. So we can look at how this is going to work. When we have base 10, as I mentioned, we have 10 different symbols. We can start counting 1, 2, 3, and so on. We can start counting in base 2, but when we start with 1, and then we move on to, well, we can't use 2, so we have to move on to 10. And then the next number will have to be 1, 1. I shouldn't even call them 10 and 11. It's really 1, 0 followed by 1, 1. And what are they equal to? Well, 1, 0 is equal to 2 in base 10, 1, 1 is equal to 3 in base 10, and so on. And so by the time we get down to 8, which we can describe as a quantity with only 1 digit in base 10, we need to use 4 digits to describe it in base 2. And each of the digits corresponds to 2 raised to a power. So if I have only 1 digit, as I do when I'm describing 1 in base 10, which is 1 in base 2 as well, what that really equals is 1 times 2 raised to the 0 power. Now you know that anything raised to the 0 power is 1, so that just means 1. So as I go on, I need more digits, and so, for example, when I get down to looking at 6, okay, base 10, then I need to describe that as 110. And what that is 1 times 10 to the second, which is 4, plus 1 times 2 to the first, sorry, 1 times 2 to the second, which is 4, plus 1 times 2 to the first, which is 2, plus 0 times 2 to the 0, which is 0. So it's 4 plus 2 plus 0, which is 6. So as it is that each of these, I'm using place value, but instead of the places being based on 10, they're now based on 2. It's very helpful to be able to convert between decimal and binary representations of numbers. Let's look at an example. Let's say we have the number 106 and we'd like to know how it would be written in base 2 or binary. The way we look at this is we try to break this number up and describe it in terms of numbers that are powers of 2. The largest power of 2 that fits into 106 is 64, which is equal to 2 raised to the 7th power. So if we subtract that from 106, we're left with 42. So that means we can represent 106 as the sum of 64 and 42. Then we look at 42 and say, well, okay, the largest power of 2 that fits into 42 is 32, which is 2 to the 5th. And then we're left with 10. And 10 we can write as 8, which is 2 to the 3rd, plus 2, which is 2 to the 1st. And we can express each one of these as 2 raised to a power. You can do this with any integer. And then further, we can express it as 1 or 0 times each of the powers. So I'm not just including the ones that are explicitly in the sum, 2 to the 6th, 2 to the 5th, 2 to the 3rd, and 2 to the 1st, but I'm also including 2 to the 4th. Of course, that term isn't in the sum, so I say it's 0 times 2 to the 4th. And then 2 to the 2nd. That also is not in the sum, so it's 0 times 2 to the 2nd. Okay? And 0 times 2 to the 0th, right? So then if we look at this and notice what is multiplied by each of the powers, we can use that as the digit. 1, 1, 0, 1, 0, 1, 0. I enclose this in parentheses with the 2 subscript to indicate that this is a base 2 number. Otherwise, if we don't do this, it's ambiguous. If you just showed me that number, that string of 1s and 0s, I wouldn't know. I could think that it was a base 10 number, because that's usually what it is when I'm looking at math. I can't tell. So enclosing it in the 2 indicates it's base 2. So that's how we would write 106 in binary. Now let's say we wanted to go the other way. We start off with a number that's in base 2, and we'd like to know how to write that in decimal representation. Well, we can expand it out. You do the reverse of what we were doing before and just say, okay, so we know that the rightmost digit is the 2 to the 0 place, and then we go move to the left, 2 to the first, 2 squared, 2 to the third. And then we're left with 1 times 2 to the third is 8, plus 1 times 2 squared is 4, plus 0 times 2 to the first is 0, plus 1 times 2 to the 0th is 1. And then all these numbers added up will give us 13. So that's what it equals. So we can see that it's much more compact for us as readers to see a number written in base 10. It's actually hard for us to read numbers that are in base 2 because it's just a string of 1s and 0s, and it's hard to kind of parse it out and keep track of what everything is. But it's much better for a computer. Computers don't care how long a string of numbers is. They execute instructions so rapidly that having, say, a number represented in base 2 that needs 50 characters to represent it is not a big deal. The advantage of this representation is it can be represented physically by using a series of switches, a bank of switches, where you just say, well, the ones that are on are represented by 1, and the ones that are off are represented by 0. So let's go back to this question. What is the significance of 1023? Well, 1023 can be represented as a sum of numbers, all of which are powers of 2. And in fact, you see 512 is the first term, that's 2 to the 9th. And every term that's a power of 2 is included in the sum all the way down to 2 to the 0 power. This can be written in base 2 as a string of 1s. In fact, 10 ones in a row, written compactly. So we actually we can represent the number 1023 in a register that has 10 places where all of the characters are binary. That is, they could be either on or off. In this case, they're all on, and this is in base 2. So what we're doing here is we're using an analog pin to read some voltage between 0 and 5 volts, and we're using 10 binary digits to do it. There's a place, a register, where this value is stored, and it has 10 binary digits or bits. 0 volts corresponds to every single one of those 10 bits set to 0, and 5 volts corresponds to every one of the bits set to 1. So that means that 0 to 5 volts is represented by a string of 10 binary digits that are a combination of 1s and 0s. So this means that if we get the value of 0, we know that it means 0 volts. And we know that if we get 1023, that means it's 5 volts. But what happens if we have some other voltage that's detected? Well, it's going to be some integer, okay, that's going to be returned that can be represented by a 10-bit number in the register. It'll be a 10-digit binary number. But we'd like to know how to relate these things to each other. So how do we do that? We know that 5 volts corresponds to 1023. We'd like to know what some arbitrary voltage that's somewhere between 0 and 5 corresponds to. What integer value would that correspond to? We can use these proportions, this relation, to develop an expression that will help us obtain the value of n. So this is what it is. Now, if I take x and it's 0.7 volts, how is that represented? I just take the 0.7, I multiply it by 1023, I divide by 5, and then I take the integer part of that, which is the part of the number returned that's to the left of the decimal point. In this case, we see that 143.22, the integer part is 143. So that is the value of n that we get back. That's what's going to be returned, and that's what the value is that the Nano will detect for us. If we use analog read and it's detecting a voltage of 0.7 volts, it's going to return 143 to tell us that. If instead the voltage is 3.2, we use the same expression to obtain the analog read return value, and in this case, when we multiply 3.2 times 1023 and divide it by 5, the integer part of the expression is 654. So you see that this is a case where even though it's closer to 655, it doesn't matter. We take the integer part, and that's the value that's used. So this means that every voltage between 0 and 5 volts is represented by an integer between 0 and 1023, and we just need to understand how to interpret what this is.